thanks for the introduction. So my name is Jérome Lesaint. I am from the University of Grenoble and the University of Lyon, and I'm going to present a preliminary investigation on the. Can I have it in the screen? Okay, I don't have the slides on the screen, but okay. Yeah, okay. And I'm going to present a preliminary study on consistency-based auto-calibration of the spectral model in dual energy CT. This is a work I've carried out with Simon Ritt in Creatis in Lyon. So the dual energy CT is, the basic principle is this one. We have an object which we model by its linear attenuation coefficient, mu, which we illuminate with two different spectra. So we get two different sinograms. So yeah, I should mention that all this work is in 2D parallel geometry. So we get two sinograms at low energy and high energy. And if we reconstruct these two sinograms, we get some, with any reconstruction algorithm, we get some reconstruction, polychromatic reconstruction with spectral artifacts in them, known as beam hardening artifacts, for instance. Okay. So the linear attenuation coefficients, it's been known for a long time that we can write it as a linear combination of a few energy-dependent functions. So it could be, as Peter Noel said earlier on, it could be two photoelectric or Compton effect, two physical effects, or it could be two material-specific energy functions, which we call FM here. And the goal of dual energy is to recover these, the spatial maps of each material, AM. And the other goal is to recover some virtual monochromatic images. Oops, sorry. So yeah, so this work is clearly a projection-based two-step decomposition. What we want to achieve is to decompose our energy sinograms into material-specific sinograms, okay? And the material basis we will be using in this work will be water and bone. Right, so now this is the forward model, and the decomposition problem consists, as I mentioned, in we want to decompose the materials, the energy sinogram SB, into the material-specific sinograms. So we don't want to recover the AM maps, the spatial maps directly, but only those line integrals. So we want to recover the material sinograms AM from the energy measurement SB. And this is an inverse problem. We have this forward problem and we want to inverse that problem. And of course, we need the effective spectrum, which is the emission spectrum of the tube multiplied by the detector response. Right, so there are a few ways of doing that. First, if you know a priori the effective spectrum, which can be calibrated with a monochromatic beam or with a gamma source, you can, if you have this prior information, then you can just address the problem as a standard inverse problem approach. If you don't have the spectrum, the effective spectrum, you can also jointly estimate in one single instance of an inverse problem, jointly estimate both the spectrum, the effective spectrum, and the sinograms. Another line is to, instead of taking a standard inverse problem approach, is to try to approximate the inverse mapping with a parametric model, okay, typically a polynomial model. And then the parametric model is learned from a set of calibration measurements. In this work, what we try to achieve is to estimate this polynomial estimation of the inverse mapping, but without any calibration, simply using the data consistency conditions. Right, so this is the formalism that we'll have for a polynomial model. So what we want to achieve, to estimate is this inverse problem from the energy measurement. We want to recover the material-specific sinograms, and we want to estimate the polynomial coefficients with the analysis of the consistency conditions, plus we still need a small a priori knowledge on the object. So the consistency condition we'll be using here, since we are in a 2D parallel geometry, we will be simply using the Helgason-Ludwig consistency conditions at order 0, which says that if we have a sinogram AM, if it is consistent, then if you take the integral of one projection, it is independent of the projection angle. Okay, so if you take this function j of theta, theta being the projection angle, and compute the integral of each projection, this function is a constant function. Okay, so what we're going to so to have a more insight in it. So on the left-hand side, this is a low energy sinogram. And if we plot the corresponding function, so for each projection, each line, each row of that sinogram, you take the integral and plot the corresponding curve, you get the red curve. Okay, and since the red curve is not consistent, we can say that the low energy sinogram is not consistent, which is expected since we have a spectrum. On the contrary, on the right-hand side, this is the water sinogram, the pure water sinogram, which was used for the simulation. And if we compute the same function, this sinogram is consistent, okay? And since it is consistent, the corresponding function is constant. Right, so what we are going to do is we are going to enforce the consistency on the material-specific sinograms, on the water and bone sinograms, and we will also enforce this consistency on the virtual monochromatic sinograms. And this is, so we measure this constantness with the variance of the function j, that I showed. And we are going to minimize this cost function with respect to the polynomial coefficients. Of course, there is a trivial solution to that minimization problem, which is the null sinogram. So in order to expect the null sinogram, which is perfectly consistent, we need to constrain the problem. So we will give ourselves two reference voxels, one for which we know it is a pure water voxel, and another voxel for which we know it is a pure bone voxel. And then the minimization problem becomes a constrained minimization problem. Okay, so in order to compare the performance of our method, we compare our results to a standard calibration-based method. So I will quickly describe this calibration-based decomposition. So we still need to estimate this polynomial model, and this will be done with a set of calibration measurements. So this is done by probing a set of combinations of thicknesses of each material. So this is, for instance, a calibration phantom. Each piece of plastic is made of 2 layers of materials mimicking the basis materials that you need, for instance, water and bone. And you can play with all the different pieces to have multiple combinations of thicknesses of bone and water. Okay, so then you probe these different combinations, and from that set of measurements, you can calibrate, meaning you can fit the polynomial model onto these measurements. Okay, so this is quite long and tedious. It can take up to 45 minutes to calibrate this, and this needs to be done at each operation setup. But this will be our reference method. So the simulation, as I showed that earlier on, but we have this object, which is a water of cylinder with a low contrast feature and 5 bone inserts. And the 2 small inserts that you have outside the big cylinder is the voxel reference that the a priori knowledge that we have on the object. We illuminate with the 2 spectra at 80 keV and 120 keV, get the sinograms and the polychromatic reconstructions. Then we feed our sinograms, we feed our consistency minimizer with the 2 polychromatic sinograms and the constraints to get some polynomial coefficients, which once applied to the energy sinograms, we get the material-specific sinograms. And then, using any reconstruction algorithm, we get the 2 material maps. Okay, so let's have a look at a closer look at the images that we get. So these are the water map on the left and the bone map. So as you can see, we achieve fairly well the material discrimination. Okay, we don't have any more. The water and bone is correctly separated in the 2 maps. But though it's not perfect, we still see some capping artifact on the water map. If we have a closer look to the profiles along the red line segments, we can see that the low feature contrast, the low contrast feature can be recovered fairly well here, but still we have some capping and some crosstalks between the two materials. Here we have a lack of signal here and corresponding to an excess of signal in the corresponding bone map. Okay. Now, as I said in the beginning, in the introduction, we also want to generate some monochromatic images. So these are the monochromatic images that we get. And so on the left, they are the polychromatic images. In the middle are monochromatic images. And on the right, the calibration reference method. Okay, so as you can see, we have achieved to reduce significantly the artifacts that were used, the beam hardening artifacts that were present in the polychromatic images. Okay, so as a conclusion, I presented a calibration-free material decomposition projection in the projection space. We enforced consistency both on the material sinograms and on the virtual monoenergetic sinograms. So we solve only one single optimization problem instead of two independent problems. The fact that we enforce the consistency on the virtual monoenergetic make the problem we need to jointly estimate the polynomial coefficients. We still need, of course, a small a priori knowledge on the object. And as I mentioned in the beginning, it's a proof of concept, it's a preliminary work, and it paves the way to further investigation. And that is it. Thank you.
This talk is now open for questions.
Yes, nice talk. I wonder about your cost function, because you have the variance or the consistency of the water sinogram, the consistency of the bone sinogram, and then you add a couple of more sinograms with energies. But since we are in dual energy, CT, and we only have two effects in your phantom, like photo and Compton effect, the consistency of the water and of the bone sinogram should be sufficient. Once they are completely consistent, the energy sinograms should have a variance of 0 as well. So can you maybe comment on this? Do I see something wrong, or because basically all sinograms are a linear combination of the first two ones?
Yes, you're right. Yeah. Absolutely. The fact is that we could not manage to separate water and bone without enforcing the consistency on the virtual monoenergetic sinograms. Because it's really the problem is really ill-posed. And if we look at only one problem, which is the estimation of the water polynomial, and if you have a look at the cost function, it's a long valley. So in terms of optimization, it didn't work. Actually, empirically, it didn't work. And when we add the consistency on the virtual monoenergetic, then eventually it worked, probably because we had some cross information between the two materials.
Thank you.
Any other questions?
I might have missed it, but so with this, I mean, it's nice work. And with the calibration, does it handle pixel to pixel variations? You often see that.
No, yeah. It's a global approach of combining the global sinograms. It's not pixel ones.
Okay, let's thank the speaker again.
Okay.